ओके हम लोगों ने वैलेंस बॉन्ड थ्योरी कर लिया था ना कि फिनिश द वैलेंस बॉन्ड थ्योरी और उसमें हमने करा कि कैसे हम इलेक्ट्रॉन्स को डाल रहे हैं, how what are the outer d complexes, what are the inner d complexes. We also did limitations of the valence bond theory. So just remember a few points from your competition point of view over here to see whether the complex that is outer d complex or inner d complex. There are a few points which I am going to tell you today. The first one is that for Mn positive ions, all those Mn positive ions which have 1, 2 or 3 electrons, 1, 2 or 3 electrons in the 3D, ठीक है, in the 3D they are going to form inner orbital complex. Right? So all those Mn positive ions which are going to have 1, 2 or 3 electrons in the 3D, they are going to form inner orbital complex. Number 2, which have D8, D9 configurations, they form outer orbital complex. Now you know that the inner orbital complex that is going to be low spin and the outer orbital complex that is going to be high spin. So in other words we can say that all those which have in D 1, 2 or 3 electrons, that is going to be a low spin complex, whereas D8 and D9 configurations is going to be high spin complex. ठीक है? फिर उसके बाद the third point which you should remember over here is that which have D4, D5 and D6 configurations. They may have both. They may form either inner or outer depending upon the kind of the ligand and the central metal atom. Okay, so D4, D5, D6, they may form both. They may form either inner or they may form either outer. Then if we are having complexes of platinum, palladium, nickel and gold in the +2 oxidation state, having D8 complexes or D8 configuration, they mostly form square planar complexes. Right? So all those, that is platinum 2 positive, Pb 2 positive, Ni 2 positive and Au 2 positive, which are having D8 configuration, they are going to form square planar complexes, and all those which have D0, D5 and D10, these are the configurations if present, then they are going to form tetrahedral complexes. Okay? So these are certain shortcuts or some points for you to manipulate the kind of complexes which are going to be formed. So with this we finish our valence bond theory. The second theory which we are going to discuss today, that is known as CFT or it is known as the crystal field theory. So we go on to CFT. Or crystal field theory. Now what is the basic difference between the valence bond theory and the crystal field theory which we are going to discuss over here? In case of valence bond theory, we saw that the bonding between the central metal atom and the ligands, that was purely covalent, isn't it? We said that the ligands, they are going to donate electrons to the central metal atom, as a result of which they are going to form the coordinate bonds. So they are more specifically, or we say that the bonds, they are going to be covalent. But over here, according to this crystal field theory, the ligands, they are going to behave as you can say point charges. Why do they behave as as point charges because they have either negative charge due to extra electrons which are present, or they may have lone pair of electrons which again are going to be negatively charged. So because of that, in the crystal field theory, it was proposed that the interaction between the central metal atom and that of the ligands, that is going to be purely electrostatic in nature. Okay, so let's just go on to this theory. This theory was proposed by H. Bethe, the name of the scientist, and Van Vleck. Now what does this theory says? Initially this theory that was applied to the ionic crystals to explain their optical properties, right? Why do ionic crystals they show color? Why do ionic crystals they are going to reflect light? Why do ionic crystals have high refractive indices? So this theory very well explained all these facts about the ionic crystals. That is the reason why it is given the name crystal field theory. Okay. After that, as I just told you that the valence bond theory that is going to give us one, you can say the bonding between the central metal atom and that of the ligands, that is going to be purely covalent in nature. According to CFT, it is going to be point charges and the forces of attraction that is going to be electrostatic. Now we also studied when we were doing the limitations of VPT that VPT was not very clearly explained about the outer orbital complex and the inner orbital complex, or it did not explain about many substances, magnetic properties. It did not explain the high spin complexes and the low spin complexes. So all that was very beautifully explained by the crystal field theory. Right? So when we doing over here, we say that the CFT or the crystal field theory that is going to give us very satisfactory explanations about the outer D, inner D, about the high spin, low spin and the magnetic properties of all the coordinate complexes. Okay? So let's just go on to the main points of the crystal field theory. The first point is that the bonding between the ligand and the complex that is going to be purely electrostatic in nature. Okay? So this was the first assumption. Now it is seen that according to this theory, the ligands they behave as point charges. And we know that the ligands they are of two types. One which we have is negatively charged ligands, right? So they are known as negative point charges. For example, we have F negative, we have Cl negative, we have Cl negative. All of these they are going to be known as negative point charges. And if the molecules are regarded, or if the molecules they are neutral, for example we have NH3, we have water. Okay, so if they are neutral, they are regarded as point dipoles, where the lone pair of electrons or the charged particle that is going to be directed towards the central metal atom. Because over here the bonding is because of what? It is going to be because of the negative charge. And over here the bonding is because of what? The bonding is going to be because of the lone pair of electrons. So there is going to be certain dipole which is going to be created if they are going to be neutral. And the negative charge will also point towards the central metal atom, and the dipole over here which is created, that is also going to point towards the central metal atom. Why? Because the central metal atom that is going to be positively charged, and secondly it also has vacant d orbitals. Okay? So this is the first point. Let's go on to the second point of CFT. According to this point, the arrangement of ligands around the central metal atom or the central metal ion is such that the repulsions between the negative charges and the dipoles should be minimum. So you know that at one time, if we're talking of coordination number of 6, there are 6 ligands which are going to approach the central metal atom. All the ligands, they are going to be negatively charged, or all the ligands, they are going to have lone pair of electrons. It is but obvious that there is going to be repulsion which will take place. So in a coordination polyhedra, as we had discussed earlier, the ligands, they are going to place themselves in such a manner that the repulsion between them, that should be minimum. So as a result of which we get 3 structures. One is the tetrahedral, which we had discussed already. The second one, that is square planar. Both of them have coordination number of 4. And we have octahedral, which is going to have a coordination number of 6. Okay? Then we come to the third point, that the interaction between positively charged nucleus of the central atom and the ion, that is going to be of 2 types. So we have 2 types of forces which are in operation over here. There are 2 types of forces. The first type of force which we have, they are the attractive forces. Now where are these attractive forces? They can be applied. The attractive forces, that is going to be between the positive metal ion, right, and between the ligands, charged ligands, whether they are negative or they are the polar neutral molecules. So the first type of forces which we have, that is going to be attractive forces of attraction. For example, if we are taking over here one compound, FeCN whole 6 3 negative. So over here, cyano, that is going to be a negatively charged ligand. The forces of attraction, that is going to be between the Fe3 positive ions and Ca negative ions, isn't it? And if we are taking another example of another complex over here, chromium 6 3 positive. Now in this case, the forces of attraction, that is going to be between the chromium and negatively charged ends of ammonia molecule. The negatively charged ends of ammonia molecule is going to be nitrogen because it has the lone pair of electrons. So the forces of attraction are between Cr3 positive and ammonia molecule, with nitrogen being directed towards chromium. Okay? So this is what we have. Now over here, the bonds between both of them, that is going to be purely ionic. It is but obvious because the central metal atom is positively charged and the ligand, that is negatively charged. So the bonds, they are going to be ionic, right? So in this theory, there is no orbital overlapping taking place as it was taking place in valence bond theory. There is no orbital overlapping which is going to take place over here. Okay? Then the second type of forces which we have. Second type of forces which we have, they are going to be repulsive forces. Okay? So repulsive forces, they are going to arise between the lone pair of ligands and the electrons in the d-orbitals. Because when we were looking at the valence bond theory, there were electrons which were present in the d-orbitals. So repulsive forces are between the electrons of the ligands and the electrons in the d orbitals. Okay, so this is the forces of repulsion which is going to take place. So the forces which are going to cause, or which are causing, or which are responsible for these repulsive forces, what is going to happen? The repulsive forces, they are going to lower down the energy of the complex, and hence it is going to increase the stability. right? So it is, you know that when we're talking of d orbitals, how many orbitals are present over there? There are 5 d orbitals, right? So when we are going to the fourth point over here, we know that there are 5 d orbitals which are going to be present. So these 5 d orbitals, they are going to, you can say, be divided into 2 sets. How many, which 5 d orbitals are present? We have dxy, we have dyz, we have dxz, dx square minus y square and dz square. So all these 5, they are going to be divided into 2 steps or 2 sets depending upon the orientation of the d orbital. So what are we saying over here? We are saying that the d orbitals, they are divided into 2 sets depending upon the orientation of the d orbitals. ठीक है? How the d orbitals, they are going to be oriented. Let's say that what are these, let's see what are these 2 sets over here. What are these 2 sets which we are going to discuss over here? Now over here we say that the first set that consists of dxy, dyz and dxz orbitals. The 3 orbitals amongst 5 which orient in the regions between coordinate axes. ठीक है? So they are going to orient in between coordinate axes. And what are these coordinate axes? They are going to be x, y and z, right? In between the coordinate axes, and these are said to be T2G orbitals, right? So they are said to be T2G orbitals. Now these orbitals, they are going to be non-axial in nature. They are going to be non-axial. What do you understand by non-axial? That they will be in between the axis x, y. When we are talking of x, y, that there are 2 lobes of D. You know this, na? There are 2 lobes of D. X, y means that the lobes, they are in between x and y. ठीक है? Y, z means that the 2 lobes, they are in between y and z. And xz means that the 1 lobe that is going to be between x and z. So they are not going to be on the axis. Therefore, they are said to be non-axial in nature. Right? Then when we are talking of the second set of orbitals, that is dx square minus y square and dz square. Both of these, they orient along the axis. They are going to orient, see over here we are saying that they are going to orient in between the coordinate axis. They are going to orient along the axis. Orient along the axis. Okay. So if they are orienting along the axis, it means these orbitals, they are known as EG and they are said to be axial. I'll just draw for you both of these, so you that then you can, compare the axial and non-axial behavior. This is the z axis, this is y, or let's say this is x, this is y and this is going to be z. So dx square minus y square कहाँ पे lie करता है? On the x and y axis. So that is why it is going to be known as axial, because they are orienting along the axis. When you are looking at dz over here, it is a donut shape. This is z over here. Okay. So this is orienting along the z axis. Therefore, it is known as axial. So the ones which are not orienting along the axis but are orienting in between the axis, they are known as T2G. There are 3 orbitals, and the other one they are known as EG, and they are going to be 2 orbitals. And these are known as axial, the other ones they are going to be known as non-axial. Is it clear? Now, what are we saying? What is happening over here? We say that whenever there is an independent central metal atom present, all the 5 orbitals of D, they are going to be at the same energy level. If they are at the same energy level, they are said to be a set of degenerate orbitals. Okay? So we are saying that for an individual central metal atom, all the 5 D orbitals, they are present as the same energy level, and they are said to be a set of degenerate orbitals. Now when the ligands they are going to approach, what is going to happen? The electrons of the D block, they are, or the D orbitals, they are going to be repelled by the electrons of the ligands. Okay? As a result of which the energy that is going to increase. But still, all the 5 orbitals, they are going to be at the same energy level. So this is for an individual. When the ligands start approaching, the electrons which are present in this, they are going to be repelled by the electrons present in the ligands. So all these orbitals, they go to a higher energy level. Okay. Now the ligands which are approaching, what will happen? The ligands may approach either in the direction of the orientation, right? We are saying that here the orientation that is going to be in between coordinate. Here orientation is going to be along the coordinates. So we say that the ligands, they may approach either in the direction or they may approach in opposite directions. So if they are approaching in the direction of the electrons which are present in the D block, then there is going to be splitting of these orbitals which are taking place according to what we have seen over here. So we have now 2 sets. One is going to be at a higher energy level. The higher energy level, that is dx square minus y square and dz square. These are going to be known as Eg, and we have dxy, dyz and dxz, which are known as T2G orbitals. Okay, so this is what is happening. When the ligands they are approaching, the electrons get repelled, as a result of which all the orbitals they go to a higher energy level. Then the D orbitals, they are going to split into 2 sets of orbitals having different energies. This is known as crystal field splitting. So basically, what is crystal field splitting? Crystal field splitting is the splitting of the D orbitals in different energy levels on approach of ligands. Okay? So that is what crystal field splitting is. Now the extent of splitting, that is going to depend upon 2 factors. One, that is going to be the number of ligands which are approaching, and number 2, the type of ligands which are approaching. Okay, so these are the 2 factors on which it is going to depend. Now let's talk of splitting of d orbitals in octahedral complexes. So this is what we have drawn over here. This is going to be splitting in octahedral complexes. Okay, so let's go on to splitting in octahedral complexes over here. Now when we are drawing any octahedral complex, let's say that this is the central metal. We have the ligand, right? And all the ligands, they are going to have a negative charge. Right? So all the ligands, what they are having a negative charge. Let's say this is going to be a coordinate which is the z coordinate. Okay? Then we have this coordinate as the y coordinate. Okay? And this coordinate over here, that is going to be the x coordinate. So you can see over here now, there are 3 ligands. That is, in fact there are 4 ligands. Z which are on the coordinates, x, y and z. All those which are, you can say, rotating or which are approaching towards the coordinates, that is going to result in splitting of the d orbital. So we'll just write down a few points over here. Number 1, electrons of d orbitals of the metal are repelled by the negative point charges of the ligand. By the negative point charges of the ligand. Number 2, if all the ligands approaching, if all the ligands approaching the metal are at equal distance, the energy of each of the 5 orbitals increase by the same amount. So that is what we have written over here, we've done over here. Okay? The energy of all the d orbitals increase by the same amount. Now this is going to be hypothetical. Why? Because the ligands approaching the cation, they cannot be at equal distances. Okay? So the third point you have to write down. Third point, if as the lobes of dx square minus y square and dz square point directly towards the ligands, the repulsions are going to be more. Okay? So because the repulsions are more, they are going to go to a higher energy level and we have Eg orbitals. Right? Then next point, if an electron is nearer to the electron pairs of the ligands than in dxy, dxz or dyz orbitals, with lobes pointing in between the ligands, with lobes pointing in between the ligands, then the repulsion is going to be less. Right? So that is how the T2G, they are going to be at a lesser energy level. Now what is the splitting energy over here? It is seen that the energy for the splitting energy for T2G, that is 2 by 5 delta naught, where naught over here or over here that represent octahedral complexes, and the energy between this, that is going to be 3 by 5 delta naught. But remember that the average splitting energy that will be a constant. So if you are adding up the splitting energy over here, 3 by 5 plus 2 by 5, that will become equal to 1. So the average splitting energy, that is going to be the same. And this is known as what? This is known as crystal field splitting energy, or it is also known as crystal field stabilizing energy. Right? So the splitting energy which we have calculated over here as 1, 2 by 5 for T2G and 3 by 5 for EG, this is known as the crystal field splitting energy. Okay? Is it clear? So the total energy of the d orbitals will not change. That is how the splitting should always take place. There should be no change in total amount of energy of d. Now the 3 orbitals, as we just said, that the 3 orbitals, they are 2.5 delta naught lower than the d orbitals, and the other one that is going to be 3/5 delta naught higher than the d orbitals. So this is what crystal field splitting in octahedral complexes is. Now let's go on to crystal field splitting in tetrahedral complexes. Crystal field splitting in tetrahedral complexes. Now in case of tetrahedral complexes, the 3 d orbitals, that is the T2g. In this case, the T2g orbitals, they are close to each other or to the approaching ligands. So as a result, what will happen? The T2g electrons, they are going to suffer more repulsions because they are closer to the ligands, right? So in this case, the T2g, the energy of T2g is going to increase more than Eg. So it's going to be opposite. In that case, what was happening? Eg was at a higher energy level and T2g was at a lower energy level. Over here, T2g is going to be at a higher energy level and Eg, that is going to be at a lower energy level, right? So in this case, the energy of T2g increases more than Eg, right? Now this, the energy gap in this, that is going to be represented by delta T, as we were representing it by delta naught in case of octahedral, where T over here stands for tetrahedral. Okay? Now when we are taking a relationship between delta T and delta naught, it is going to be equal to delta T, that is equal to 4/9 delta naught. Is it clear? Then we come to crystal field splitting in square planar. Here things are going to be very complicated. Now when we are talking of square planar complexes, in this case the arrangement of 4 ligands around the central metal atom, this is what going to happen over here, right? So what is happening? When we are talking of square planar complex, there are going to be 2 ligands less than the octahedral complex in case of square planar. So if you are drawing an octahedral complex in which there are 2 axial positions which are given, there are no axial positions which are present in square planar. So we have over here 2 positions less than the octahedral position, right? So both these ligands, if you just see the diagram which you drawn before, the axis which we were drawing over here was the z axis in case of octahedral. So 2 ligands, they are missing from the z axis. Okay, now what will happen because of this? Because of this, dz square dxz and dyz, all of these 3 orbitals, they are going to have only one z component. They are going to have only one z component, which is going to be more stable. Okay? All of these 3, they have a z component which is going to be more stable. Okay, then the octahedral complexes. Now what happens to the lobes of dx square minus y square? Dx square minus y square, that is going to point towards the ligands. And this is going to have the highest energy. Because they are pointing towards the ligand, so the repulsion is going to be the maximum over here. So it will have the highest energy. Okay? And the lobes of dxy, when we are talking of lobes of dxy over here, they lie in between between the ligands. So it is next highest energy. So let's try and draw this and understand it better over here. So if we're taking over here D, we have D, 1, 2, 3, ठीक है, 4 और 5, right? These are going to go to a higher energy level. 1, 2, 3, 4 and 5. Now how does the splitting take place over here? We have again 2 Eg and 3 T2G. Now these are going to further split up now. So when we're talking of this, these are further going to split up in this dx square minus y square. That is going to go to a higher energy level. Okay, and dz square to a lower energy level. So this is dx square minus y square. This is going to be dz square. Okay? And when we're talking of T2G over here, one goes at a higher energy level and two are at a lower energy level. So the one which is at a higher energy level, that is going to be dxy and dxz and dyz. That is going to be a low energy level. So if you get a question to write down the order of energies in square field splitting or square planar complexes, then the order that is going to be dxz is equal to dyz is less than dz square is less than dxy is less than dx square minus y square. So this is a different splitting than what we have done in case of octahedral. Okay, that is why this is happening in case of dxy and dxz and dyz. That is, these are not going to be affected at all by the electrostatic field of the ligands. That is why their energy, that is the lowest. Okay, कितनी कोई भी एक किसी भी एक d orbital की फील्ड कितनी इफेक्ट होती है by approachment of ligands, उसके basis पे the splitting that is going to take place. Clear? Then we come to another important concept over here, spectrochemical series. Now there are two types of ligands which are present. When we talking of ligands, ligands which are going to bring about more splitting of the d orbitals, they are said to be strong field ligands. Okay. So those who are going to get more splitting, that is these ligands, they can approach the central metal atom with greater ease. Right? So because they can approach the central metal atom with greater ease, as a result of which they are going to bring about more splitting and they are known as strong field. And those which approach the central metal atom with difficulty, they are going to cause less splitting and they are known as weak field ligands. Okay? Now the spectrochemical series that gives us an arrangement of the ligands. Spectrochemical series, it gives us the arrangement of ligands in order of increasing field splitting, increasing crystal field splitting. ठीक है? कि कितना कोई भी एक लिगेंड स्प्लिटिंग कॉज कर सकता है, उसकी इंक्रीजिंग ऑर्डर में हम जब आयंस को या मॉलिक्यूल्स हैविंग लोन पेयर ऑफ इलेक्ट्रॉन्स को अरेंज करते हैं, दैट इज गोइंग टू बी नोन एज स्पेक्ट्रोकेमिकल सीरीज. सो दिस इज इंपॉर्टेंट फॉर यू बिकॉज ओनली दिस कैन हेल्प अस to know that how much splitting is going to take place, whether pairing will take place or not, or whether the complex that is going to be low spin or high spin. Okay? So let's see over here the spectrochemical series. We are going from weak field to strong field. So iodine has a weak field, weakest field ligand. Okay? Then we have bromide, then we have chloride, nitrate, F negative, उसके बाद OH negative, oxalato. After oxalato is H2O. H2O is generally taken as the center. So after H2O, all the strong field ligands they are going to begin. So we have H2O, then we have pyridine, which is going to be equal to ammonia over here. Then we have ethylene diamine. Then we have dipyridine. Then we have orthophenyl, right? And after orthophenyl we have NO2 negative. Then we have cyano and the carbonyl, which is going to have the maximum splitting capacity. So all these below, they are going to be weak field ligands, and all these they are going to be strong field ligands. Okay? Is it clear? So strong field ligands, they are going to cause greater crystal field splitting, and weak field ligands, they are going to cause less crystal field splitting. Apart from these, there are certain other factors on which the crystal field splitting may depend. Number one, it will depend upon the position of transition element in the periodic table. Right? So what is the position of transition element in the periodic table? On that also crystal field splitting that is going to depend. So if we are going down the group, the crystal field splitting for octahedral complex increases down the group. Right? For example, if you are taking Ni2 positive and we are taking Pt2 positive. So nickel belongs to the 3D series and platinum that is going to belong to the 5D series. Okay, so we're going down the group over here. It is observed that platinum complexes, they are going to have large crystal field splitting. Here, so as you're going down the group, the crystal field splitting that is going to increase. Then number two, it will when we are, in fact, there's a number which is given to us when we're going down the group. It is seen that for the second transition series, the crystal field splitting is almost 50% more than the first transition series. Okay, so nickel or platinum there's going to be a difference of 50%. And the third transition series is about 25% higher than the second transition series. Is it clear? Then the second, it will also depend upon the oxidation state of the central metal ion. It will depend upon the oxidation state of the central metal ion. Generally the ones which have higher oxidation state, they are going to cause more crystal field splitting. So if you're talking of CO2 positive and CO3 positive, CO3 positive is going to cause greater number of splitting. Then third, it will also depend upon the number of ligands which are going to approach the central metal atom, and it is seen that crystal field splitting for tetrahedral complexes, that is 4 upon 9 that of octahedral complexes. So more the number of ligands, more is going to be the crystal field splitting. Is it clear? So let's now distribute the electrons in case of T2G and EG. So we're talking of complexes of the type D4. Okay? So we are taking complexes of the type D4, which means it has 4 electrons in D4, in the D orbitals. First of all, we are going to take the distribution if the ligand that is going to be weak field ligand. So we know that the weak field ligand that is going to cause less splitting. If this is T2G, the energy difference between the T2G and EG, that is going to be less. So as a result of that, Hund's rule of maximum multiplicity that is going to be followed if weak field ligands are present. That means that pairing will not take place until unless each of the ligand that has been singly filled. Right? So the fourth electron can easily enter into the EG because the energy difference in this case that is going to be less. Now there is another kind of energy which we discussed over here, which is the pairing energy. Right? So over here, the value of delta naught, this is the value of delta naught which we have. Okay, over here the value of delta naught, that is going to be less than pairing energy. Because the value of delta naught is less than pairing energy, therefore no pairing will take place in such type of complexes. Okay, and complexes over here, as you can see that the complexes, the electrons, they are filled up in 2 different levels of orbitals. So, and all of them, they are going to be unpaired over here. They are going to form high spin complexes, right? And as all of them, they are unpaired, so they are going to form paramagnetic substances. Now just see a comparison with the strong field ligand over here. When we're looking at the comparison, in case of strong field ligand, you see that the crystal field splitting that is going to be more than that in the weak field ligands. Okay? So as a result, the filling up of orbitals take place against the Hund's rule of maximum multiplicity, where pairing that is going to take place at the T2G level only. Okay, now over here, what is going to happen? The crystal field splitting energy that is going to be greater than pairing energy, therefore pairing that is going to take place over here. Okay, this is going to form a low spin complex, and of course it is going to be paramagnetic with 2 unpaired electrons. Paramagnetic with 2 unpaired electrons. Okay, now over here you need to remember that if the complex is D1, D2 and D3, and of course D0 also, it does not matter whether the ligand is strong field or it is going to be weak field. The same is going to be the case for D8, D9 and D10. So for all these complexes, the approachment of the kind of ligand is not going to be important. Right? So it is going to have the same arrangement for both strong field as well as weak field ligands. Then when we are talking of D4, D5, D6 and D7, over here the arrangement will depend upon the kind of ligand, whether it is strong field or it is weak field. Is it clear? So in case of weak field ligand, the number of unpaired electrons are always going to be more. In case of strong field ligand, the number of unpaired electrons, they are always going to be less. समझ आ गया? Now over here, how will you calculate the crystal field splitting energy, which is more commonly known as CFSE, crystal field splitting energy, that can be calculated with a formula of minus 0.4x plus 0.6y delta naught, where x, that is going to be equal to number of electrons occupying T2g orbitals, number of electrons occupying T2g orbitals, and y is number of electrons occupying EG orbitals. Okay, so this is how you can calculate crystal field splitting energy. जितनी ज़्यादा नेगेटिव होती है CFSE, उतना ही ज़्यादा स्टेबल होगा कंपाउंड. Lower the value of crystal field splitting energy, more stable is going to be the compound. So this is all about crystal field splitting. We are only left with one lesson over here in which we are going to discuss the color, the magnetic properties, and we have another topic in your syllabus, which is the metal carbonyls. That generally I've seen that comes in your competitions. Organometallic compounds, that is not in your syllabus. So we left with 3 small topics over here, which we will be discussing in our class lesson, and then we start with organic chemistry. ठीक है?